Hello, my name is Aditya Pillai, and this is my lab report on Lab 1, Concept Velocity. The objective of this lab was to analyze the velocity and motion of an object when there are seemingly no net forces acting on it. Analysis of the object's motion could be done through observation in comparison with the predicted model. In order to do this, we were to familiarize ourselves with the programs Tracker and GlowScript. Tracker to collect observed data, and GlowScript to model predicted motion. In the process of doing this, we were to apply key physics concepts we had learned in class. Some of the key physics concepts that were applied during this lab include Newton's first and second laws of motion. The first law states that an object in motion or rest will remain in this state unless acted on by its surroundings, and the second law states that the force on an object can be measured by the change in the object's velocity over time multiplied by its mass. Other concepts applied include the momentum principle, the velocity update formula, and the position update formula. This is the video that I analyzed in Tracker. It is a roll of duct tape rolling at what appears to be a concept velocity with no observed net forces acting on it. This segment was selected because before there was some force from the initial push to get it rolling, and afterwards it fell off the table and had another net force acting on it. The origin of the axis was set at the center of the object when the clip began, and the duct tape roll itself was used to calibrate the length measurements. Points were set at the observed center of mass in each frame during the clip, and the graph itself appears to be nearly straight, though at some points it does look bent. From Tracker, we get a set of data points which gives us information on the initial position, which is 1.938 times 10 to the negative 4 in the x direction, and the change in time over the clip, which is 2.292 seconds. The mass of the object, which we weighed beforehand, is 1/10 of a kilogram. We can calculate the initial velocity from the data given from Tracker using the first and second point and the time elapsed between these points. Doing so, we get the initial velocity to be 0.383 meters per second. Using the momentum principle, which states that the change in momentum is equal to F net multiplied by the change in time, we can derive the velocity update formula, which states that the final velocity is equal to the initial velocity plus F net divided by mass multiplied by the change in time. Plugging in these values, we get 0.383 meters per second as the final velocity as well. The velocity should remain constant in accordance with Newton's first law of motion if the net force on the object is actually zero. Using the position update formula, which states that the final position is equal to the initial position plus v average times delta t, in this case v average being 0.383 meters per second because F net is equal to 0, we get 0.878 meters as being the final predicted position of our object. When creating the GlowScript model, the starter code needed to be altered to fit the lab. Changes include setting the mass of the object to 0.1 kilograms, setting the initial position and the initial velocity, changing the final t value to the length of the analyzed video, and updating the ball's velocity and position update lines so they'd properly represent the velocity update formula and the position update formula. This is what the code looks like when it's run. When the graphs of the observed points in comparison to the predicted points are seen together, it becomes quite clear that the observed and predicted positions are different near the end of the time frame. Though they may start off similar, this graph makes the curve and observed position more clear than the graph in Tracker, especially when compared to the predicted position. This, as well as the graph of the observed and predicted velocities, demonstrates that there was some form of net force acting on the object, most likely including friction and drag. As we have the measurement of the velocity near the end and the beginning, the change in time, and the mass of the object, we can calculate the average net force on the object during this time, which we get to be 0.008 newtons. There were two questions posed to us before we started the lab. The first one being, when you analyzed your video in Tracker, you made your choice of the orientation of the axes. Discuss briefly how your results would change or remain the same if you were to flip your axes. The answer is simple. If my axes were flipped, the same distance would be traveled, but in the negative x direction, meaning that it would be moving to the left. The speed would remain the same, but the velocity would change direction. The position versus time graph would have the same slope magnitude, except it would be negative. The other question was, your observation can be predicted well by your computation model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? Discuss briefly. The answer is a bit more complicated. We can't determine the individual forces regardless, as there are many different variations of fundamental interactions. Even assuming just fundamental interactions, it is extremely difficult to account for forces such as drag, friction, gravity, and electrical force, which would have effects so minute they may not even be possible to calculate. Having a sum of the forces of an object through observation means that we don't have any information on the individual forces to try and quantify them. In conclusion, while it seemed like the object was moving at a constant velocity, the predicted data and observed data differ from the result of non-zero forces acting on the system. Newton's second law could be observed through the motion of the object and was used to quantify the net force that acted on it over the time period. Newton's first law was helpful in creating a prediction, though the prediction was a bit inaccurate because net forces were present in the system.